those together, take the square root, would equal 0.05. If you had 500 people in each group, 500 people with a risk of 10%, 500 people with a risk of 5%, again, the average of all those risk differences from study to study should be average out to about 5%, but now the standard deviation in those numbers would be 0.0166. And if you had 50 people with risks of 50% and 45%, this is what you'd expect, a mean of 0.05 for a sampling distribution with a standard deviation of 0.09. And 500 people with those same risks would have the same average with a smaller standard deviation of 0.03. So notice the standard deviations of these sampling distributions, what we refer to as a standard error, gets smaller as your n gets bigger. And just to convince yourself of that, what I did is I ran some simulations in SAS. I did 200 studies, each with 50 people. This is scenario 1, 50 people with a risk of 10%, 50 people with a risk of 5%. I calculated their risk difference. I wrote it on a piece of paper. I went back and simulated another study, a different 50 people with a risk of 10% and a different 50 people with a risk of 5%. Calculated the risk difference from that study, wrote that on a piece of paper, and did it 200 times. What did I get? Well, one study gave me a risk difference that was as small as minus 0.08. Another one gave me a risk difference that was as big as 0.2. But on average, the 200 studies gave me the average risk difference of 0.04, very similar to the 0.05 that we would expect, theoretically. And the standard deviation of those 200 numbers was 0.04909, which was very similar to the 0.0524, which I expect theoretically. And finally, if I drew a histogram of those 200 risk differences, it sort of looks like a bell-shaped curve. This is a stem and leaf diagram that we talked about before on its side. If I looked at scenario number 2 with more people, 500 people with a risk of 10% and 500 people with a risk of 5%, calculated the risk difference in that study, and then did it 200 times. Now notice the risk difference is 0.04. The standard deviation is now smaller. This scenario 2, excuse me. The risk difference is still around 5%, but the standard deviation is getting smaller because the sample size increases. There's 500 people in each group. And again, the distribution looks bell-shaped. So what that means is that theoretically, what I predict was going to happen is supported by these simulations. So I can use these theoretically sampling distributions to be the basis of sample size calculations, because let me just jump ahead a few slides. This is what I'd expect for a sampling distribution under the null hypothesis for the risk differences. On average, the average of all those risk differences from all those studies would be 0. It would have a bell-shaped curve, as suggested by these computer simulations. And I could define a test of significance. I could say, I'm going to reject the null hypothesis. If I get a value for a risk difference that's bigger than a certain value or smaller than a certain value, where these vertical lines here represent some values, that beyond those values, there's a certain percentage of studies, say 5%, alpha equal 5%, of studies that are that large in a positive sense or that large in a negative sense. So this is how I would describe the sampling distribution, how I might do a test of significance by finding a cut point that gave me a tail probability of 5%, 2.5% in the positive tail and 2.5% in the negative tail. Now, if the alternative hypothesis is true, if there was a non-zero, I'd have a bell-shaped curve, same width, same spread, but would no longer be centered at 0, it would be centered at the true value for the risk difference, say positive 0.2. But now I could talk about using that test of significance, that same cut point. I could talk about the probability of making the other type of mistake when I do a test of significance, a beta error, of not rejecting the null hypothesis when the alternative hypothesis is true. And that's the area under the second curve, the second distribution to the right of that sampling, of that cut point. So if I put them two together, I'd say for a given sample size, I have two sampling distributions, one if the null hypothesis is true and one if the non-null hypothesis is true. One of them distributions, the solid one, can describe the basis for the alpha error for a test of significance, and the dotted curve would tell me the beta error. And the point is, we knew from the previous slides that when n gets bigger, these curves get narrower, and when n gets smaller, these curves get spread out more. So I could find an n that would give me, say I fix alpha at 0.05, I could find the n that would give me a certain value for beta. Or if I wanted to fix the value of beta, I could find that would tell me what the n would be to give me that particular pair of curves. So the bottom line is that when you do sample size calculations, essentially what you're doing is considering sampling distributions. Typically, we fix the value of the test as significant at 0.05. Typically, we say we're going to do a two-sided test of significance. And we have two options. We can fix the value of beta, say at 10% or 20%. In other words, saying that if we fix beta at 10%, we want 1 minus beta, our power, to be 90% for detecting that alternative hypothesis. Or if our beta is 20%, we're fixing the power at 1 minus 20% to be 80%. And we can figure out what is the size of n, what is the sample size that will give us that value of beta, or that value of power. Or the alternative, we could fix the value for the sample size and figure out what beta corresponds to that particular sample size. So that's all we're doing most times when we're doing tests, when we're doing sample size calculations. They're based on tests of significance. They're based on comparing sampling distributions. When the null hypothesis is true, when the non-null hypothesis is true, on those sampling distributions, locating the cut point that defines a significant result corresponding to a value for alpha, usually at 0.05, and that determines the value for beta if our sample size is fixed, or if we determine the value of beta, that determines the n that would give us that beta. I should add there is some sample size calculations that are not based on tests of significance, and those are usually based on confidence intervals. So it's still based on sampling distributions. But today let's talk about sample size calculations based on tests of significance. And I'm going to show you in a minute a software package that SAS has for an add-on that allows you to calculate sample sizes or calculate power. You fix the power, it gives you the sample size, or you fix the sample size and it tells you the power. It's called the PSS, the Power and Sample Size Application. It's not a procedure in SAS, it's actually software that uses two procedures that SAS has. It's proc power that it uses, or proc GLM power. I've never read about those procedures, and I haven't used this software package that much, or this interface. It's based on using the Microsoft Internet Explorer, and it basically, here's a link if you want to read more about it. But the point is, this is one of many. You can go on Google today and search sample size, and it'll link you to other software packages you can use for free. This is a free add-on if you have SAS. I get it through the School of Public Health here at Harvard. But there are many other freebies you can get off the web. UCLA has a nice one. Vanderbilt has a nice one. University of California, San Francisco has a nice one. All these will do pretty much what this will do. So let me show you how this works, just to show you an example. So I'm going to minimize this.